in the online mode, and our topic of focus is module number 5. In module number 5, today we will discuss upon the on-off control, then principle of phase control, and also R and RL load. We will not be discussing today TRIAC as a light dimmer today, right now. Maybe one more session might be required to complete that. Also, the one single phase induction speed controller. So, whatever I'm marking in blue, that will be completing today. Also, we'll be starting with principle of cycloconverter operation, and we will be discussing single phase to single phase step up and step down cycloconverters. Again, introduction to three-phase cycloconverter. I leave it to the, let's see whether we get another lecture to cover this topic. So these are the topics we will be covering. Mostly 80% of module number 5 will be covering today. 70% maybe. So let us begin. Are the screens and whatever I'm marking clear to you? Yeah.
Yes, sir.
Okay, fine. So there are two types of AC voltage controller. It's called as AC voltage controller. So it's also called as AC to AC converter. Okay, so last category, module number 5. In these two types, we have two categories: AC voltage regulator and we have a cycloconverter. So let us now understand what is the difference between AC voltage regulator and cycloconverter. So in case of AC voltage regulator, we have a fixed AC voltage, and we can have a fixed amplitude and a fixed frequency, right? For a AC signal, we will have a fixed amplitude and fixed frequency. But in our case, in case of AC voltage regulator, the output will be variable. Now, how it will be variable? Either you can vary volt amplitude or frequency. So here we keep frequency fixed, but we vary the amplitude of the output signal. Is that clear? So we vary the amplitude and keeping the frequency fixed. So that's why it's called as a AC voltage controller. Input is AC, output is also AC, but it's a variable AC. Okay. So these kinds of controllers are used in room heaters, right? Speed control of fan, that is single phase induction motor. So all these controllers are used over there. Then we have a cycloconverter. Again, we are converting fixed frequency into a variable frequency. But now, here, earlier in AC voltage controller, we had at the output fixed frequency. In cycloconverter, we can have a variable frequency as well as a variable amplitude. So that is what is called as a cycloconverter. So in cycloconverter, there are two categories. Number one is step-up cycloconverter. So in step-up cycloconverter, the output frequency is greater than the input frequency. Both are AC, remember. Okay. And in step-down cycloconverter, the output frequency is less than the input frequency. Okay. So this is the category. So if they ask you what is a cycloconverter, so you can say it converts a fixed AC, that is a fixed amplitude and a voltage, into a variable AC, that is a variable frequency and amplitude. And there are two types: step up and step down cycloconverter. Is this clear to you? And some of the
Sir.
applications are similar, that speed control of AC motor, induction heating, and static VAR compensation. Okay, reactive power compensation. Sorry, anyone has any doubt? Okay, fine. Now we'll start with principle of phase control. Actually, this principle of phase control we have already discussed in the control rectifier part, but again I'm repeating. So your SCR is so operated such that the load gets connected to the AC source. Okay, so we can consider a single half wave rectifier also to demonstrate this, but in generally this is what is happening. So we have a firing angle alpha, and we control when do we start the SCR, right? So part of each half cycle of the input gets connected to the load, and a part of each cycle of the input gets connected to the load as per the phase, right? As per the deciding angle, that is alpha. All right. So this is principle of phase control, And in principle of phase control, we will be studying two types of AC voltage controller. We'll be studying half wave, and then we'll be studying full wave AC voltage controller with R and RL load. Actually, in your syllabus is mentioned only single phase full wave AC voltage controller. Half wave is not mentioned. But without half wave, full wave is little difficult to understand. Not difficult, but it's necessary that we should discuss half wave also. So I'll briefly discuss half wave AC voltage controller with R and RL load next. Okay, fine. So this is done. Now we'll be starting with its topic is single phase unidirectional AC voltage controller. Okay. So it's also called as unidirectional AC voltage controller, or we can call it as a half wave AC voltage controller. The working is pretty simple over here. Here we have one SCR, and then we have an anti-parallel a diode and a resistor. So this kind of controller is a resistive load. So here we have R load. Okay. So what will happen during the positive half cycle? During the positive half cycle, T1 SCR is forward bias or in the forward blocking mode, but it's not conducting. All right. When it gets the gate trigger pulse, only then it will start conducting. All right. That means your positive half cycle can be controlled because SCR is a control device. What natural commutation, and diode D1 becomes forward bias. Okay, diode D1 become forward bias, but it instantly turns on. So this is what will happen. So from the period 0 to, let me go over here. So this is my AC waveform. So from 0 to alpha, none of the devices are on. I mean, D1 is off, T1 is also off. So at the output, you will have a zero voltage because current is not flowing. I out is zero, both are off. Now, as soon as you apply alpha, that is the triggering gate pulse, your T1 turns on. So as soon as the T1 turns on, the picture looks like this. So your input source is getting connected to the load via T1 SCR. All right. So here I out is equal to I in, output load current is equal to input CRT1 turns off at omega t equal to pi due to natural commutation because its voltage is going negative. All right. As soon as the T1 becomes reverse bias, it turns off. Now, what happens in a negative half cycle? In a negative half cycle, D1 is forward bias. Okay, because this is positive, this is negative. So here the polarity comes like this. So it will forward bias the diode and it will start conducting. Now it will start conducting, it will be on for the entire period from pi to 2 pi, right? So here I out will be equal to I out and I in both are in the reverse direction. V out will be equal to V in, that is also in the reverse direction because we are talking about negative half cycle. So in a negative half cycle, as you can see, there is no control at all. As soon as the diode turns on, the output will follow the input. All right. Where is you can see the control over here in case of positive half cycle. And since it is a resistive load, the current waveform, this is I out current waveform. Actually, that is also equal to I in waveform. I out and I in waveform are one and the same. Okay. This is I out equal to I in. All right. And in the resistive load, output load current and waveforms are same. And again, during this time, SCR is again re-triggered at 2 pi plus, 2 pi plus alpha, and then the whole thing repeats itself. So we can calculate the average value. It's not necessary, but I'm just showing you the formula. I told you this is not explicitly asked in the syllabus, but it comes under the category of principle of phase control. So they can ask it there. That's why I'm covering it. So we have done many times this V out average, right? So average value of the output waveform we have to calculate till t. This is t from year to year. That is from 0 to 2 pi. So 2 pi is the period because it then it repeats. All right. So here we can apply from 0 to alpha, your output is 0. So the integral limits will go from alpha to 2 pi. And you can plug in the values over here. 2 pi value is minus 1. And here the average value of the output is load voltage is Vm upon 2 pi into cos alpha minus 1. Similarly, the output current average will be Vm upon 2 pi r. On the same lines, you can calculate V out RMS. I am not discussing that in detail. We have done this many times. You can note down the formula for the V out RMS, or it is already there for reference. Rather than discussing this, we'll cover the important topics. Is that okay? And I out RMS will be V out RMS upon R. Okay. So what does it tell you? It tells you that the output RMS value is a function of alpha. So as you vary the alpha, we can control the V out RMS value. But there is a problem with this type of AC voltage controller. Can anyone highlight what is the problem in this circuit that leads to bidirectional AC voltage controller? Can anyone identify what could be the problem? Okay, the problem is, listen, it's a, I'll just explain that. It's a AC to AC converter, right? Whether it's a amplitude control or frequency control doesn't matter. So maybe it's a variable AC. So when do you call it as a AC signal? When the average value of this AC signal is 0. Let's say this is V1. Whenever V1 average is equal to 0, that means V1 average is your DC component, right? Whenever DC component is equal to 0, we can call it as a pure sine wave. But over here, if you can see carefully, your V out average is not 0, all right? And your I out average is also not 0. So there is a DC component in the output. So DC current may cause input transformer to saturate. Sometimes we use the transformer because the voltages are pretty large, right? So I out average or V out average contains a DC component. Can you hear me? Hello,
Sure.
hello. In
Yes,
between,
sir.
I was not audible.
Yes, sir.
Now it's fine.
Yes, sir.
Okay, where I have missed, I mean, where you couldn't hear me, what point was being discussed? Can you just tell me? Hello?
I think you were discussing that V out average part when you were explaining the diode, the circuit part.
Acha, this one.
Yes, sir.
Okay, okay. Yeah. So I was explaining there is a drawback to this circuit, half wave control. I mean, half wave AC voltage controller. The drawback is that it is a AC to AC converter. All right. We are getting a variable AC by controlling the voltage. But since it's a AC, its average value of a AC signal should be 0. That means if this is V1, your V1 average should be 0 because V1 average component represents a DC component. And if a DC component in a AC signal is 0, then it's a pure AC signal. All right. So over here, we can see V out average and I out average are not equal to 0. So that means there is a presence of DC component in the AC output. So therefore, if we use a transformer to step down input voltages, so here we have I out average as a DC. So transformer doesn't work with DC well. So it will saturate the transformer. So this drawback is eliminated by the bidirectional controller. Okay. So here, what are the learnings from this? In a single phase half wave AC voltage controller, only positive half cycle can be controlled, negative half cycle cannot be controlled. So it is also called as single phase unidirectional voltage controller. Is that fine? As you can see from the waveforms, only positive half cycle can be controlled. Negative half cycle you cannot control because you cannot control the diode when it turns on. It instantly turns on when it is forward bias. Whereas in SCR, you can control when it turns on. Okay, it is clear? Any doubt in this before I proceed? It is not explicitly mentioned in the syllabus, this topic, but it comes under principle of phase control. So under that category, I'm teaching this. So I don't think so they will ask RL load. So I'm just completing R load. I mean, in fact, this topic is only not written. Is that fine? Any doubts in this?
No, sir.
Please let me know quickly. Okay, very good.
So basically the waveforms will be the same, right? V out, IG, I out, and VM by R, right? So for this
Yeah.
circuit for
Now,
you.
yeah. Now concentrate on this. This is more important. That one was just explaining the concept of AC voltage controller. Okay. All right. So here you can note down the circuit diagram till the time I explain you the concept. So this circuit is pretty important. They normally ask this, for 5 marks or even 10 marks for along with the waveforms and the expressions of the output average volt, average and RMS value. But this is pretty important. Okay. So here what do we have? We have a AC input and we are expecting a AC output, right? Which is a variable AC output, maybe amplitude variation. It is amplitude variation. Here we have two SCRs connected in anti-parallel mode. Okay, so two SCRs connected in anti-parallel mode. Do you remember any power electronics device which is bidirectional? Do you remember any device which is bidirectional? Anyone? Any device which you have studied?
Triac.
Right, right.
Uh, this is diag. Correct, na?
Yes, sir.
Three terminals it has. So what happens? It does the same functionality, but why are we not using the triac? Because in power electronics, SCR is the king. SCR is the major device because it is used for extremely high power application. The ratings of the SCR are the highest, right? So we are using two SCRs in anti-parallel, but the same circuit can use a triac when we require medium or low power application. So triac will have uh, low ratings or power ratings. So here we are using triac. So that is used in fan regulator. You remember your fan regulator, you rotate your fan regulator to change the speed. So internally, what is happening? The potentiometer resistance is changing. So basically, what are you doing? You are changing the firing angle of the track at which it conducts. So that's how it will control the speed. Did you understand now? Same
Ye-
circuit, you can replace SCR by a triac because fan regulator is not a high power application. It's a low and medium power application. So that's why we don't use triac over here. We could use triac, but we are discussing a high power application. So for that, we can use two SCRs in anti-parallel. The ratings of the SCR are almost twice or thrice than the rating of the triac. So triac is faster, SCR is slower, but SCR can sustain high voltages. But triac is meant for low and medium power application. Did you understand with clarity now? Can we begin with the working?
Yes.
Okay. So what will happen? You tell me now. In the positive half cycle, T1 is forward bias, eligible to turn on. Okay. So it turns on after alpha. Fine. And in a negative half cycle, your T2 is turning on. I mean, at pi, at omega t equal to pi, your T1 turns off naturally because input is going negative. And when will T2 turn on? T2 is eligible to turn on during the negative half cycle, but it will turn on after pi plus alpha. Okay, it will turn on after pi plus alpha. So that is what we will discuss over here. As you can see in the waveforms clearly, this is my input. These are my triggering pulses. The green color is for T1 and orange color is for T2. So at the output, as you can clearly see, from 0 to alpha, output is 0 because none of the SCRs are on. After alpha, T1 is turning on, so my output will be equal to input. Then from pi to pi plus alpha, again none of the SCRs are on. T1 has turned off over here. Okay, यहाँ पे T1 off हो गया. here. Okay. And here T2 is off naturally because the voltage is going negative. All right. So T1 turns off over here, but T2 is not turned on. So we have to wait till alpha, and again the T2 turns on. Your output follows the negative input. Okay. And then again the same thing story repeats for the subsequent half cycle. Now, one advantage which you see over here is this. It's a symmetric AC waveform, right? That means अगर इसका average voltage if you calculate, it will be zero. So that's a big advantage. That means this is a pure AC waveform, doesn't contain any DC component. And since it is a resistive load, your output average current also will be, load current also will be zero. That means there is no DC component in the signal. Is this clear to you, everyone? The working?
Sir, like
Yes
in
or
this
no?
circuit, yes, sir.
Yeah, tell me.
Uh, yes, sir, your circuit is since there are two SCRs. So in this circuit also, it is not possible to obtain a pure sine wave. There will be a line in between the two when you
Yeah,
talk about
yeah,
the
you're not
waveform.
getting a pure. Yes, you're not pure in the sense it doesn't contain any DC component. See, in power electronics, there is nothing called as a pure sine waveform. Only thing is what I meant by pure is it doesn't contain any DC component. It will definitely a voltage control, right? If you have such waveform like this, and here you decide your firing angle to be like this. Okay, your waveform how it will look like this. So this is no way like a pure sinusoidal waveform, right? But at least the average value is zero. That's what I meant. Okay, so your alpha is different. Your alpha is different. So it all depends upon your firing angle when you turn it on. Okay, so what I meant by pure is not it doesn't have any DC component. Means it's symmetric. It should be at least symmetric. Positive and negative halves should be same. Then it's easier to analyze and process. Do you understand now?
Yes, sir.
Here we are controlling the amplitude. See, it's amplitude control discussion. AC voltage controller is you get a variable DC. By changing the alpha, you can change the average, the RMS value of the output. Average value is zero. Okay. So here I have described the working from zero to alpha. This is the period from zero to alpha. Both are off. Then over here, T1 turns on when we apply the gate trigger. So output is equal to Vin. Is same thing we have explained earlier. So T1 turns off at omega t equal to um, pi due to natural commutation. Then again, in the negative half cycle, T2 is triggered on at pi plus alpha. So from pi to pi plus alpha, none of the SCRs are on. So output will be zero. And again, when T2 turns on, your output will be equal to V in the negative half cycle. So the conduction period of the T1 transistor is alpha to pi. That means the total conduction period is pi minus alpha. And the conduction period for SCR T2 is pi plus alpha to 2 pi. That is again pi minus alpha. So again the T2 turns off at omega t equal to pi plus alpha. Here there is a alpha term missing due to natural commutation. Oh, sorry. It should be 2 pi. Okay, it should be 2 pi, not pi. I'll correct those changes. So due to natural commutation. All right. And since it is a resistive load, your load current waveforms are same. All right. Now, can you see this VT1, VT2? What is VT1, VT2? Anyone? Is the voltage across the thyristor 1 and voltage across the thyristor 2. Now, here you will be wondering, there is one surprise here. The surprise is that when the SCR is off, your voltage across the SCR will follow the input, right? So here it is following. When the SCR is on, your voltage across the SCR will be very less, almost zero. But the question is, what is happening in the negative half here? Why is this happening over here in this side? Why it is behaving this way in this cycle? Can you explain the behavior over here? Anyone? See, these two SCRs are connected in anti-parallel mode, correct? So when one is on, other is off. So uska voltage will appear over here. All right. So during this period, from pi to pi plus alpha, none of the SCRs are on. So it will follow the input. Then your SCR2 will turn on. So when SCR2 turns on, what will be the voltage across SCR1? Same as SCR2, right? But almost zero, right? So here it is zero, as you can see. So that's why the behavior like this. And similarly for VT2, same behavior will depict, but in a reverse direction. So I hope you have understood about VT1 and VT2 behavior. It's not that key when they are off, completely the output is zero. You see there is a parallel SCR also connected, anti-parallel mein SCR also connected. Okay. What about the current flowing through the SCR? So yeah, current flowing through that SCR, let's say we talk about SCR number one, T1, right? So it will have the same nature, but during the negative half cycle, there is no current flowing through that SCR, right? So current will be zero. The current will only flow when your SCR is on. So T1 is on over here, T1 is on over here. So it will only flow whenever the particular SCR is on, T1 is on, right? So if you have to derive this formula, this is similar to a semi-converter, half controlled, I mean, not semi-converter, half controlled converter, right? So here the limits can be from alpha to pi, because 0 to 2 pi, if we consider, pi to 2 pi is 0, because output is, I mean, current is 0. So you consider alpha to pi, and it's pretty easy. The output, I mean, the expression comes out to be Vm upon 2 pi r into 1 plus cos alpha. All right. Now, anyone have any doubt in this before I proceed? Quickly, please tell. Any doubts in this? Yeah. So as it is a symmetric waveform, I told you the average output value is zero. Average load current is zero. So this suggests that your output is a pure AC signal. Don't meant by a pure AC signal means without any this thing. Pure in the sense it doesn't contain a DC component. Okay, its RMS value can be determined as follows. So integral is from 0 to t 1 upon t Vm square sine omega square d omega t raised to half. So where t over here is you can consider to be pi, and from alpha to pi it goes from limits from alpha to pi, and then you can solve this and you will get this expression of V out RMS, that is Vm upon root 2 into 1 upon pi into 2 pi minus alpha plus sine 2 pi upon alpha, bracket close, the whole raised to half. Okay, so here we can see that you can control the V out RMS by controlling the firing angle alpha, and your RMS load current will be V out RMS upon R. Okay, so they can ask you about the derivation, that is V out RMS derivation. Then if they ask you for 10 marks, you have to draw all the waveforms. It's pretty simple, as you can see. It's very easy actually. AC to AC voltage controller. Okay, no need not draw these diagrams. I've just given it for your understanding only. Okay, so let us see what learnings we have seen over here in a single phase full wave AC voltage controller, or is also called as single phase bidirectional voltage controller. Now this is the term which they have mentioned in the syllabus. Single phase bidirectional voltage controller. So the circuit which we have discussed is this only. Its other name is phase controlled converter. So here we have both positive as well as negative half cycle can be controlled, of course. The phase relationship between the start of the load current and the supply voltage control can be varied by finding angle alpha. That is very, very obvious. The waveform really reveals that the positive half cycle is identical with the negative half cycle for both the load voltage and the load current. And it doesn't introduce any DC component in the supply. So the circuit turn-off time is pi upon omega. It's helpful for solving the numerical. But remember, V out and I out are not exactly like looking like a sine wave. It has this small period where it is zero. All right. So since they are symmetric and average value is zero, we can determine the Fourier series also easily. So yeah, this is slightly, you have to note it down somewhere. So the Fourier series of the output will be your positive and negative half are identical. So your DC component is absent, even your even harmonics are absent. That means n is 1, 3, 5. So summation of n equal to odd numbers, Vm upon pi into sine of n plus 1 alpha upon n plus 1 minus sine of n minus alpha upon n plus n minus 1. So here we cannot determine n equal to 1. So n equal to 1, that is a fundamental component V1 it has to be determined separately. So here is the formula given for V1. Similarly, I1 will be amplitude of fundamental component of load current, that is V1 upon RL, which is the load given. So these two expressions you have to take care. If they ask you, you have to solve this. Derivations are not expected. Only the formulas have to be remembered. Okay. There is some note I have written over here. Why the fundamental component is very very important. So when AC voltage controller is used for speed control application. Okay. So here we have a speed control application of single phase induction motor. Only the fundamental component is useful. Okay, whereas the harmonics in the system is responsible for increasing the losses, heating, reduce efficiency, and so on and so forth. Okay, so the harmonics will cause the noise and the vibration in the motor, but for heating and lightning applications or loads, both fundamental and harmonics are useful. Okay, so V out RMS would be known to you for producing the AC controlled power. Okay, so that's it about the single phase bidirectional AC voltage controller with R load. Any doubts in this? Anyone? Let me know quickly so that I can continue. Okay. Next is numerical. I'll just go through the numerical. We will not get the time to solve it. Okay. Here is the numerical. We should do all the numericals and go. You better be prepared. Okay, so here they have given it's a numerical on single full wave AC voltage controller. So read the question carefully. Where R is 20 ohms, input supply is 230, 50 hertz. So this is a VM or a V in RMS? Is it a RMS value or peak value? 230 volts.
Peak value.
No, it's RMS value. If it is not mentioned by default, it's a RMS value. And the firing angle of both the SCR is 45. How this is possible? How the firing angle is 45 for both the SCRs. One SCR is conducting at alpha, other SCR is conducting at pi plus alpha. So that will be 180 plus alpha. Okay, so that way they are saying the both firing angle is same. So you have to calculate the RMS value of the output voltage, that is V out RMS, then the output load power P out, which is V out R, I mean we can consider as I out RMS square into R, then the input power factor and average currents of the SCR. So please complete this numerical whenever you get the time. Right now just go through it. Just listen along with me. So here they have given the V in RMS value. So VM will be 230 root 2. Alpha is 45, converted into radians, it will be pi by 4. So conversion factor is pi by 180. Remember that. Now, V out RMS formula is given, straightforward calculations are there. You substitute all the values, VMS to 230, then alpha. Here, alpha has to be substituted in radians. Huh? You should understand where it has to be substituted in radians. So, here it has to be substituted in radians. Whenever alpha is with sine and cos, substitute in degree, else in radians. So, this V out RMS is coming out to be 219.3. You can check it out. Then P out, output power is I out square RMS into RL. I out square RMS is V out square upon RL square, right? So here it comes out to be 2400 watts. I out RMS is same as I in RMS. So that is V out RMS upon RL. That will be around 10.9 amperes. Power factor is P out upon V in RMS into I in RMS. So I in RMS is given, V in RMS is 230. So here the power factor is coming out to be 0.95. So it's a good power factor because anything closer to 1 is very good. and IT average, that is the average value of current flowing through the SCRs. Formula is 1 upon 2 pi into RL into cos into 1 plus cos alpha. So put in the values of VM, it is 230 root 2, RL is 20, alpha is 45. So you'll get the current flowing through the SCR is 4.4187 amperes. So that is how you solve one numerical on AC voltage controller, bidirectional AC voltage controller. Is this clear? Yeah. Any doubts? Okay. Next, we go on to the next one. The single phase. Again, we have single phase AC voltage controller with a R load, and the supply voltage is same. So this is V in RMS value. We have to calculate the maximum value of average SCR currents for any firing angle alpha, then minimum circuit turn-off time for any firing angle alpha, and the first harmonic for alpha equal to pi by 3. So remember one thing, the formula for the average SCR current will be Vm upon 2 pi r into 1 plus cos alpha. And here the maximum value of average SCR current will be occurring at alpha equal to 0. Okay, so calculate this at alpha equal to 0, you will get 34.51 amperes. All right. Then T of time is given by the formula pi upon omega. It's independent of alpha. So pi upon 2 pi f. F is around 50. So it's 1 upon 100. So it's around 10 milliseconds. Okay, pretty straightforward. Then the first harmonic or the fundamental component is given by this formula. Plug in all the values. You will get an answer close to 272.967 volts. Okay, I'm going a little fast because important topics are to be covered yet. So is the numericals okay? Did you understand? Are you able to solve it on your own? Or will you be able to solve it on your own? Yes?
Yes, sir.
Okay, great. So I'll move on now. Okay. Just now we have covered and studied and understood single phase full wave AC voltage controller with R load. And now we are going to discuss its complementary form, that is RL load. Very, very straightforward. So what will be the difference between the previous one and this one? In this one, your earlier your SCR1, when it was conducting, it was stopping its conduction at alpha. But now it will continue to conduct till beta. Why? Anyone? Because of the inductor. The inductor will allow the SCR to conduct further till beta. And what is beta called as? Anyone remembers? Extension angle, right? I'm not able to write that. Okay. Extension angle. Okay, so here we have done explicitly study of why does the inductor allow the SCR to conduct till beta. Okay, so right now let us concentrate on how does it affect the circuit operation. So exactly the same way the circuit will operate. Only thing is you have to take care of inductor, right? So what happens in the first case? From 0 to alpha, nothing changes. Both the SCRs are off, so output is 0. Then alpha arrives, your T1 and turns on, and it should stop at pi, but it will continue in the negative direction because of the inductor stored energy. And once it reaches a beta value, here it is. I'll just concentrate over here. Yeah, once it reaches a beta value, see, beta should be less than your pi plus alpha. Okay, so you select your firing angle in such a way that the extinction angle is first, and then the firing angle comes for the next SCR, because the other SCR should be turned off before the next SCR is turned on, right? So over here there is beta. So till beta, your output value will continue. Wait a second. Okay. Yeah. So y'all can see right over here. This is still beta. Okay, this is the value beta, and up till here your output is following the input, and then from beta to pi plus alpha, none of the SCRs are conducting. But SCR number T2 is eligible to turn on. So when a triggering pulse arrive at pi plus alpha, your SCR T2 will turn on and it will follow the input. Again, it will conduct till pi plus beta, right? Now from pi plus beta to 2 pi plus alpha, none of the SCRs are on. So at 2 pi plus alpha, SCR T2, I mean T1 will conduct and the cycle will repeat itself. So that's the only difference between your R and RL load. And also the current, why does the SCR turn off? Not due to natural commutation, but only due to the fact that your output current is reducing to zero. So as you can see, after alpha, the current is building up and it decays to zero at alpha, at beta. So since the current flowing through the SCR, I out is becoming zero, that's why the SCR is turning off. Okay, not because of the negative voltage over here. So at beta, the SCR T1 will turn off, and at pi plus alpha, SCR T2 will turn on. So it will increase the current, and again at pi plus beta, T2 will turn off, and at 2 pi plus alpha, T1 again will turn on, and that is the way you will get the current, I out current. Is this clear to you? The only challenge over here is this is the difference. Okay, to understand this Vout waveform is to understand the circuit functioning. And if you are able to draw the output voltage and load current, you have understood the circuit. And now it's time to sit and write down the working in steps. That is 0 to alpha, alpha to pi, then pi to beta, then beta to pi plus alpha. Are you getting it? So the cycle nature will be similar. Here again, the circuit turn off time will be pi upon omega, and your the entire functioning I have told over here, I have explained in terms of diagrams, and this is not the first time we are discussing about RL load. So here, one statement it will conclude that due to RL load or inductive load, the SCR conduct beyond pi, 2 pi, and 3 pi. All right. So here the V out RMS value we have done it before. This thing, same thing we have repeated before for I think full converter with RL load, right? So it was similar formula you got. So you can check out the derivation for RMS value of the output voltage, V out RMS. It's important for if they ask you some numerical on it. Okay. Is this clear to you? Now there is second case also. Second case is when alpha is less than phi. Now what is phi? Phi is the difference between the, I mean, it's a RL load, right? So there will be a phase difference between the load voltage. Here it's not a load current, it should be load current. This should be I out. Okay, this should be I out. So let me add over here. Here I have to correct it out. This is I out. Okay, the green one is I out and the red one is V out. So there is a phase difference between I out and V out, right? And if we keep alpha less than this, phi phase difference, then the voltage waveform will look like this. There will be no distortion at all. Only phase difference will be there. So if alpha firing angle is kept lower than the phi, then the waveforms are looking as below. Okay, so that means your output is always Vm sin omega t. In fact, there is no control established over here because here in this formula, V out is Vm sin omega t. It's independent of alpha. It's uncontrolled. On root 2 divided by square root of r square plus omega l square. So it's like an uncontrolled circuit which we have studied in the rectifier's part. So here also, if we consider alpha to be less than phi, then yes, these are the waveforms we will be getting. Lesson part I've written over here. I guess you all can go through it right now. It seems unwise to discuss this in detail because here it is load voltage and current are not controlled. Okay, the only control it will be established is if alpha is greater than phi. And the case earlier we have discussed is alpha greater than phi. Okay, is this clear to you, everyone? Any doubt in this? so that we will move on to the last topic, that is cycloconverters. Please respond quickly. You have understood how we got this waveform? Yes, no?
Yes.
Okay, great. I know I'm letting going a little fast because the window is around 1 hour. So we have already completed 50 minutes. Now last 10 minutes are remaining. Now, now this one. Okay. So there is something called as principle of on-off control. Very, very simple. Now that you have understood the working of this bidirectional AC voltage controller. So what is this principle of on-off controller? So what we do is we keep both the SCRs on for certain number of cycles and both the SCRs off for other number of cycles. Let's say for n cycles you keep the SCRs on. So during those n cycles, V out will be equal to Vm sin omega t. And for m cycles, you keep all the SCRs off. There are only two SCRs, so both the SCRs are off. And then when both the SCRs are off, the output will be zero. All right. So this is the picture, which I mean, you all can see, right? In one, okay, one go. Yeah, this is my V in. So as you can see, there are many cycles of V in, and here alpha is zero. Huh? Alpha is zero. It's been triggered at alpha equal to 0, 2 pi, 4 pi. Then IG2, that's for T2 SCR. Uh, you know, T2 has been triggered at pi, 3 pi, then 5 pi, like this, and so on, right? So during this, as you can see, this blue period over here, it is N. So during this period, your output will be as it is, as same as your input. Okay. Then there is a phase where we don't apply any triggering pulses. So then the output will be zero. As you can see, the output is zero. So that cycle is called as M. And again, when you go to N cycle, again you apply the triggering pulses for some time. So for 3 cycles, let's say we apply the triggering pulses T1, T1, and T1, then T2, T2, and T2. Your output waveform will look like this. So from period 0 to this N, your you we can call it as an on period whenever both the SCRs are conducting. Then there is a off period equal to M, and there is again a on period, right, equal to N. So this is how alternatively we can turn off your for some application if we require that. For which application they require, we have also written that for application where the load with large time constant are required, so that current doesn't reverse rapidly. Okay, so here we have this V out to be zero for a particular period of time. It depends upon the time constants of the load application. Okay, and I out waveform will be same because it's a resistive load. So this is the principle of on off control. You keep both the SCR on for some time. I mean, alternatively you turn it on, then you keep it off, both SCR off, and then again you alternatively keep it on, so that you get this kind of a nature. So did you understand what do you mean by principle of on off control, everyone? Very, very simple, nothing great in it.
Yes, sir. Sir, can you show the circuit once?
Same circuit it is. It's just that you're controlling the firing angles. That's it. Okay.
Okay, sir, understood.
Yeah, you turn on and off during the particular period. You have to have a control. Ki when the triggering pulses will not be applied. That's the challenging part. So for first 3 cycles, you apply the triggering pulses. For next 3 cycles, you don't apply the triggering pulses. And for the next 3 cycles, again you apply the triggering pulses. So alternatively, you turn on and off. It's also called as, very famously called as integral cycle control. But in your syllabus is mentioned as principle of on-off control. See, it's not very hard. Only thing is don't get afraid by the waveform. They are very simple. If you have understood how does it operate, the topic is extremely simple and extremely marks oriented. You can definitely get this marks very easily. And then output RMS value will be Vm upon root 2 into n upon m plus n. Okay. So m upon m plus n is nothing but k, where k is the duty cycle of AC voltage controller. So simple numerical can be asked based on this also, which I will share it with you later on. I didn't get time to write. I'll share it with you, so you all can solve it on your own. Okay. So is this understood? Principle of on-off control. Now next we are moving on to the cycloconverter. Quickly, tell me if you have understood or no.
Yes, sir.
Okay, you can go through it at your own pace. I will be providing this PDFs. Okay, now very important cycloconverter. Yeah, in cycloconverter, we are going to discuss the principle, then single phase to single phase, step up, and step down. We might cover, let's say, I'll explain the concept, but we might cover in detail maybe next time. Another 1 hour or half an hour session will be required to cover the pending topic from this. Okay, so let me begin. So what we have discussed so far in the cycloconverter. What is the cycloconverter? Anyone?
AC to AC
So
converter.
no, it's a fixed AC to variable AC converter where you can convert into a variable frequency or variable amplitude. So here it has two types. Number one is step up cycloconverter. Number two is step down cycloconverter. So in step up cycloconverter, your output frequency is greater than your input frequency. And in a step down cycloconverter, your output frequency is less than your input frequency. So this we have already discussed, right? Now let us begin with the circuit diagram directly. Single phase to single phase step up bridge cycloconverter. I have taught you dual converter. No, right? I have not taught you dual converter, right? Correct. Dual converter is not yet covered. I'll cover that. Maybe one half an hour. We'll take it some other time. Not now. Today I'm winding up in next 10 minutes. So yeah, you just understand the circuit and then I'll explain how it works. So yeah, you have a single phase supply V in. You can see V in over here. This is a single phase supply. I am, let me see. Yeah, this is a single phase supply. And what is this P1, P2, P3, P4? The name deliberately we have written it as P is because they form a P converter, let's say. It's a converter, right? SCR P1 to P4. They'll be triggered in this fashion. P1, P2 together, P3, P4 together. Okay? And the same supply has been given to another set of SCRs. So, but they are in reverse direction. So here we have N1, N2, N3, N4. N1 and N2 will be working together. I mean, turning simultaneously turning on, and N3 and N4 will be turning on together. Is that fine? All right. And we have a load. We can have a resistive load. We can have a RL load also. So let us start with the working. So SCR P1 to P4 are forming a P converter, and SCR N1 to N4 are forming a N converter. You should understand how to draw the circuitry. Once you draw it perfectly well, then it will be very, very helpful and clear to you. Is this okay? Can we start with the working?
Yes, sir.
Okay. Now, during the positive half cycle, as I told you, P1 and P2 will turn on. And in the other side, N1 and N2 will turn on. So when P1 and P2 is turning on, let's see the working now in detail. So positive half cycle, it will come from here. It will go through point A, then P1, then the load, then P2, then back to supply. Okay. Now same supply has been applied to the other side. So it will go from this point, then it will come to N1. N1 is forward bias, and you apply the trigger pulse also. Then it flows to the load. See, the direction is opposite. So V out will be negative of minus V in sine omega t. Then N2 will turn on, and then back to negative part of the supply. Simple to understand. So over here, two SCRs are turning on, P1 and P2, and N1 and N2. So output is Vm sine omega t, and V out is minus Vm sine omega t. Is this clear to you? Simple working. Okay. Now let me understand the other case during the negative half cycle. So during the negative half cycle, how it goes is the polarity changes, right? So it'll go from below here, a negative half cycle, then it will go to point B. So P3 is on, then you go through the load, then P4 is on, back to the supply. Again, from the other side, you go start from the positive supply. Here it is positive. It's going through point A and then N3, then the load, then again to N4, point A and back to supply. Okay. So during this time, when P3 and P4 are on, your output voltage is equal to minus Vm sin omega t, because output itself is negative. And now you are saying the direction is from top to bottom, and top to bottom is considered as a positive, this thing. But input is negative, so your V out will be opposite of V in, that is minus Vm sin omega t. And then N3 and N4 are on. I mean, they are negative only, so an input is also negative. So that's why output is also positive. Input is negative, output is negative. So there is no sign difference. So did you understand this working? During the positive half cycle, which SCRs will be on and which will be off? Is any clarity required further in this? Yes, no. Cycloconverter, come on. You have understood or
Yes,
no?
sir. Yes, sir.
O- Okay, great. Now see. Now how to plot the waveform? First plot the input. Now let's say you want to, let's say your frequency has to be stepped up by 3. That matlab we want output frequency to be 3 times input frequency. So it's a step up cycloconverter. See, step up or step down, the circuit diagram remains the same. Okay, the circuit diagram remains the same, only what changes here I'll tell you. So let's say if you want to divide, how much is the period of this complete one cycle is the period, right? So if I divide this period by 6, okay, half period is this much, right? This is another period. So if I divide this one cycle into three parts, 1, 2, and 3, all right. So if I divide it somehow into three parts, I can have this much as T out. So as you can see, your T out is nothing but 1 upon F out, and T in is nothing but 1 upon F in. So automatically your output frequency will be 3 times greater than the input frequency, because the time period is less of the T out. Now after that, what do you do is this. So from this period to this period, your P1 SCR is conducting, and then from this period to this period, your N2, I mean these are the firing angles, huh? This period which I'm dividing with, these are the firing angles which you can say. So from here, this green portion which you see of the waveform, this is the output waveform. So from 0 to, let's say, this value, your P1 SCR is conducting, then N2 is conducting in a negative half cycle, then P1 is conducting. When N2 is conducting, output will be negative. See, yeah, N2 is conducting, output will be negative. It will follow negative. So yeah, it is negative. This is minus Vm. Then again P1 conducts. Then again N1. Now N1 conducts in a negative half cycle, and then P2, and then N1 again, and the same story will repeat. So as you can see, you are getting a higher frequency at the output, 3 times the higher frequency. So this is how the circuit functions. It's called as a bridge cycloconverter. The two SCRs will conduct simultaneously. Actually, this PDF was incomplete. I was about to write some theory, but then your lecture time started, so I stopped it. This all takes some time. Okay, so yeah, this is how you. This is the idea for a step up cycloconverter. Everyone understood?
Yes, sir.
Okay, step down. Actually, I don't have anything right now with me, so that I will cover next time. But you have understood the concept of a cycloconverter. If they ask you in the exam about write a short note on or explain single phase to single phase step up bridge cycloconverter, at least you can attempt it. Okay, you can attempt it. Circuit diagram itself will carry around some marks. So if you draw it correctly, explain it correctly, then you will get definitely at least not full but half the marks if you have not prepared. Even you have understood now, you can draw this waveform. Okay. So step down I'll cover next time. I have not written it, and I don't teach from anything else by referring the PDF. I only, whenever I write something, I only teach from there. So that I'll cover next time. Maybe when is your power electronics exam? So that
27th
will be
December, sir.
okay. Okay. So let me stop sharing this.